Hi class, sorry I can't be there today. So instead of our usual class, I'm going to ask you today to just watch these videos together with the Khan Academy videos, and hopefully that will get you through this one section on linearization. So I'm making this video in particular to give you my perspective on linearization. So our usual announcements just a reminder that you have three things due today. You have WebAssign for 3.7, which I believe is very short. Then you have WebAssign 3.8. And then you have three summary sheets, one for each of, or I guess it's four summary sheets for 3.5, 6, 7, and 8. And even though I couldn't be there in class today, I will have my usual help session tonight from 7 to 8 p.m. Then, yeah, let's jump right into linearization. So if you watch the Khan Academy videos, the essential idea boils down to this idea. So sometimes, we have a function that has maybe a very complicated or hard to compute formula. And so the idea is we would like to replace that with a simpler function that is still fairly accurate. So we can replace the complicated function nearby a point with a simpler approximation. And it turns out that there's many ways of doing this. So the idea is, and there's sort of a hierarchy of them. So there's something which I would call the zeroth order approximation. And this would be what would happen if we tried to approximate some function f of x by a constant function. So this is kind of the worst approximation that still can be useful. And so what you would do is you would say, well, suppose I have my complicated function, which I'll draw in red. And then I have a point on this graph. And then the idea is if I zoom way in on that graph, and I just replace a piece of it, then the difference between that constant function and the actual function is very small, right? And so we would say something like where this value here is f of c. So that's one thing you can do, but it turns out to not be the greatest approximation, right? Then the next best thing you could do is what's called the first order approximation. So the next best thing you could do is the first order approximation, which would approximate f of x near some value c by a line. So now instead of just being a constant function, we can take any line. So, and this turns out the line that's the best turns out to be the tangent line. And the idea is if we stay close to c, then the function stays relatively close. I mean, the farther away you go from c, the worse it gets, the farther away the line gets from the function. But if you stay close to c, it's still close. And so here the idea is we approximate the function by the tangent line near c, because this turns out to be the best approximation. But you can continue this. I'll just give you an idea. We're only going to go up to first order in this class, and we're really only going to do first order, not even worry about zeroth order. But So that's not quite true because we do 0th order when we do integration, but the 2nd order approximation, just to give you an idea of the pattern, if you want to get better approximation, is you find the best approximation to f near C using a degree two polynomial. So the idea now is that f of x will be approximately, some polynomial that looks like this. Instead of a line, it's now degree 2, right? So the order of your approximation means the degree of a polynomial you're using to approximate by. And so what you would do is now instead of using a line, you'd take a quadratic function. And it's hard to say exactly what this might look like, but it might look something like this. So you might end up with something like this, and you'll notice that it's a really good approximation here on the right, right? On the left it's a little worse, but it's still fairly good compared to our line above. Okay, and so it turns out like the higher order of the polynomial you use, the more like the function you can make it look. So linearization. The idea is that the best approximation to function f of x near a value c is the tangent line. Okay, so if we go back up to our picture, this point here would be the point c comma f of c, right? And so the formula of this tangent line would be, well, its slope will be just the derivative at c, right? The slope at a value is equal to the derivative at a value is equal to the slope of the tangent line at that point. And now we have a slope and we have a point. So we can use point slope form to write that this equation will be the derivative at the point. That's our slope, and then our y value is f of c. Okay. And this is exactly what we call the linearization. So because this is such an important idea, it gets many names. Here, when we're thinking of it as a linearization, we're just changing, instead of thinking of it graphically, we're now thinking of it as a function. So we're going to think of it as L of x, L for linearization. And so its formula is just what we had. It's the formula for the tangent line to f at the value c. Okay. And it turns out that you can prove that this is the best line in some sense. It stays the closest to the graph. Okay, and then we're going to conclude this video by doing one example. So this question is asking us to compute the linearization. So this question is asking us to use linearization, or sometimes you'll just see the words linear approximation, to approximate this cube root value, the cube root of 126. Now that's something we could just plug into our calculator. So suppose we didn't have a calculator. How could we use calculus to get a quick idea of where this number is close to? Well, the idea is, so let's remember the cube root function looks something like this. It's kind of similar to square root, but it has a left side as well, and it grows a little slower. So this is x to the 1/3 power, or also known as cube root of x. And you know, somewhere in this place there's a 125 in here somewhere. Okay, which is close to 126. And now why did I choose 125? Well, I chose it because I know that the cube root of 125 is 5, right? 5 times 5 times 5 is 125. And 125 is also close to 126. So those were the two reasons I chose it. One, because it was close to the value we're interested in, and two, because I know how to compute it. Now if I follow this up to the graph, I could draw the tangent line, and then the idea is, you know, 126 is going to be over, well, just a little bit more than 125. If we follow that up to the graph, we'll see that there's a small difference here, right? So the idea is we're going to use an approximation by taking this value, whereas the exact value would be down here. And this will be the actual. So we're talking about the y values here. And okay, so how would we actually do that computationally? So what we do is we write down the linearization at a nice place close by. So basically I'm choosing C to be 125. And then I'm using our linearization equation. And for the linearization equation we need f of C and we need f prime of C. Okay, so f of C we said was the cube root of 125. F prime of x is 1/3 x to the minus 2/3. So f prime of 125 is 1/3 times 1 over 125 to the 2/3, which we can think of as being 1 over 125 to the 1/3 power all squared, because that makes it easier to compute. So we said the cube root of 125 is 5, so 5 squared will be 25, so this ends up being 1 over 75. Okay, so our L of x is 1 over 75 times x minus our nice place nearby plus f at our nice place. So f of 125 we said was 5. Okay, so this is the linearization. And then remember, the idea is near 125, f of x is approximately the same as L of x. So we use that to say f of 126 is approximately L of 126, because 126 is close to 125, and we can now compute L of 126. So it says that this says that the cube root of 126 is approximately 5 plus 1 over 75, which makes sense. It should be a little more than 5, and this tells us roughly how much more than 170, how much more than 5 it is roughly. Now, another bit to this would be to answer the question, so our answer, this is not the exact answer, right? So we could ask, is our approximation an overestimate or an underestimate? is the number we found too big or too small compared to the actual value? And how can we figure out which of those it is without actually using a calculator? Well, the idea is all encoded in the picture we drew above. So in this picture, right, if we zoom in here, because the tangent line was on top, lied above the function, then when we plugged our 126 into our linearization, the tangent line was above, so the y value was higher there than the actual value, which would have been on the red line. So this means that our approximation was an overestimate because the tangent line was above the graph. So the answer is, this is an overestimate, since the tangent line near 125. If the tangent line had lied under the graph, it would have been an underestimate. All right, guys. Thank you for watching, and I'll see you on Thursday.